Good afternoon, everyone, and welcome to this next to final side event of the day. This has been Permafrost Day at the Cryosphere Pavilion. Last Tuesday, we released here in Baku the 2024 State of the Cryosphere report. Since a lot of people have switched out between week 1 and week 2, we wanted to repeat our presentation of the main findings of this report. The State of the Cryosphere report was started because these regions are changing so very quickly, even from year to year. But in addition to changes in observations of cryosphere, we're seeing changes in terms of the projections of what is going to happen. The research is getting better and better and more advanced. And because of that, it's seen as vital that we bring every year to negotiators as well as to the general public what has changed from year to year, what they need to be paying attention to. And this year we have a real focus on the cost of cryosphere loss in terms of not just the need for mitigation, but of course adaptation and loss and damage, which is a big focus of this COP. And so without further ado, I'm going to introduce one of the nearly 60 scientists who have worked on this report over the past several months, Dr. James Kirkham, who is the chief scientist to the Ambition on Melting Ice high-level group on sea level rise and mountain water resources, for which ICCI serves as the secretariat. So Dr. Kirkham, please.
Thanks so much, Pam, and hello everyone. Welcome to, what is it now, 6:30 p.m. in Baku. Thank you for staying this late. So we're going to walk you through the main scientific findings of this report, and I'll give it back to Pam again to talk about what the findings really mean in terms of the conclusions for the negotiations and why the science is so critical right now. Yes. Okay, so this is just a selection of some of the last news headlines in the last 12 months from the cryosphere. It's not very good news. Everything is accelerating. We're seeing extreme events we've not seen before. And this is really having a big effect on ecosystems, but also the rest of the planet. Now, the reason that we're seeing already so many of these extreme events today is that whilst we've already warmed the Earth by 1.3 degrees overall, when we look at how this compares to the average for the Arctic, we see that the polar regions are heating up much, much faster than the global average. This is about 4 times the rate for the Arctic and about twice for Antarctica and the Hindu Kush Himalaya region. Now, this is having big effects. So the year started off with a fairly comprehensive snow drought across high mountain Asia, with areas, particularly the Tarim River Basin, down by about 30%. And this is really key for agriculture, so it's the world's breadbasket. The effects were felt acutely on the ground. So this photo is from Namche Bazaar, which is the home of many of Everest's greatest mountaineers. And a personal friend of mine, Tenzin Sherpa, who is actually the grandson of the last surviving member of the first expedition to scale Everest, went home this year to this site. And he was asked by his neighbors and his friends who had lived there for decades, for the first time in living memory, why is our mountain black? For the first time in our memory. Now, just a few months later, a glacier-like outburst had ripped through the town of Tame, which is on the route to Everest. So boulders were moved, houses destroyed. It was very, very devastating. And what you can see here is just the scale of destruction. So these boulders from a pretty small glacial lake are about the size of houses, demolished schools, homes. Thankfully, it happened in a day, so no lives were taken. But you can really see that these devastating events are already affecting mountain communities today. Now, one of the biggest stories of the year in terms of mountain glaciers came from Venezuela, which became one of the first countries in modern history to lose all of its glaciers. As well as this, we saw record glacial melts confirmed by the WMO in 2023, with extreme losses, particularly in North America and Europe. Now, we can measure the amount of ice that is lost from a glacier in a fairly simple way by drilling a hole through the ice and dropping a stake in there. And the amount of ice that melts away in the coming year, we can measure by how much ice was on the stake. Now, this is Matthias Huss. He's about as tall as I am, and he's standing by a stake which shows the annual ice loss between 1950 and 1980. This is how much was lost in 2022, and again in 2023, and in 2024. So we're talking about massive ice losses in the center of the glacier, far above the ablation zone. Now, moving on to our ice sheets, and the first thing I want you to understand about these is just simply how big they are. So I've overlaid a map of Europe on the right here. So those of you in the audience who know Europe or even live in Europe, I'd encourage you to find your country on that map, marvel at the size of Antarctica, and then imagine your country being covered by a layer of ice that's almost 4 kilometers high in places. Then you get an idea about how much ice these ice sheets are really holding. Now, because everything is warming up, these ice sheets have begun to melt increasingly and lose mass over the last 20 years. These animations, these videos show the amount of ice lost in the last 20 years, and red is bad here. What we know now is that Greenland is losing ice 5 times faster than it was 30 years ago, and Antarctica is about 25% higher over the same time period. Now, because glaciers are melting and ice sheet contributions are accelerating, sea level is now rising about twice as fast as it was 30 years ago. And this is having already big impacts today. And we've seen this, for example, because it's already exacerbating the damage caused by extreme events, such as the hurricane, which have caused storm surges across the US coastline in recent months. And the science is actually getting much better at attributing the role of anthropogenic sea level rise in causing economic damage from storms and hurricanes like this. So an example from Hurricane Sandy showed that actually $8 billion of extra damage was caused because of the pollution of fossil fuels driving sea level rise to date. And as well as that, that extra bit of sea level rise, about 23 centimeters, since this real increase in fossil fuel pollution emissions, actually was the difference that caused Lower Manhattan to be flooded. So it's causing really significant damage already today. Now, this is not so surprising because we are increasingly realizing just how sensitive these ice sheets are. And some work that came out earlier this year showed that ice sheets which look like this today used to look a bit like this sometime in the past when CO2 levels were about the same as they are now. So ice cores in Greenland showing that the summit station was ice-free in the last million years, and also some evidence that parts of West Antarctica had a seaway between them during the last interglacial. So really large ice loss at quite low temperatures. We've also had a lot of updates about exactly where the damage is being done and how this is happening this year. So this is really good science, which we can use then to improve our models of future sea level rise. So how much will it rise in the future? A really good paper that came out about a month or so ago was comparing different ice sheet models, and it really highlighted the difference between low and high emissions, supporting the IPCC's summary for policy figure on the right here, which is showing that if you go on a low emissions pathway, you can keep sea level rise by 2,300 to about 0.5 meter to 3 meters. But if we continue under a high emissions pathway, we could be looking from 2 meters to 7 meters. And if these instabilities really kick off, we could not rule out 15 meters in that same time frame. So moving on to sea ice, which is really the global reflector of the Earth. It's a refrigerator that keeps the Greenland ice sheet cold and also has really important feedbacks on extreme weather and keeping the rest of the planet cool. Now, this cooling effect is being lost as the sea ice recedes. And so a paper that came out earlier showed that the cooling effect on the planet given by Arctic and Antarctic sea ice is now reduced by about 14% since the 1980s. So the solar radiation coming in is not being reflected out as efficiently as it was in the past. Now, in the Arctic, we've seen a long-term decline of sea ice, and in the Antarctic in recent years, we've also seen a shift towards a very different regime of extent. And so it may well be that we've seen regime shifts in both the Arctic and the Antarctic at just 1.3 degrees of warming. As I mentioned, Antarctica had a very strange year last year, which basically none of the models were able to replicate. And this year, that trend held the same. So again, it's strengthening this idea that something seems to have shifted in Antarctica, and the science in the next few years is going to really scramble to try and catch up and understand exactly what caused that and what the physics are behind that. Now, where do we go in the future? And the really key conclusion here is that it's still our choice. It's a really easy choice. So under low emissions or very low emissions, we can maintain some concentration of Arctic sea ice year round through the Arctic. But if we then compare this to a medium or high emission scenario, we see that we are looking at an ice-free Arctic for several months of the year in the near-term future. Moving on to permafrost, one of the big results from this year was that the Arctic boreal permafrost region is now a net source of emissions. As well as this, another study came out showing that really for permafrost in the Arctic, there is no tipping point, there is no threshold at a big regional scale, which means that every increment of temperature increase matters here. There is no danger zone which we cross some sort of threshold. It just keeps getting worse. We've also seen updates about subsea permafrost, and then again, it's the same choice of some limited thaw at low emissions in the long run, but really under high emissions, this begins to get locked in the next 60 years or so, and then will continue for really multiple centuries into the future. Finally, polar oceans are experiencing increasing amounts of acidification. CO2 levels in the atmosphere topped 428 parts per million several times this year. And again, we're faced with a really stark choice in the long run between acidifying oceans under current emissions or limiting the damage under low emissions. Although it gains a bit less attention typically than sea level rise, acidification is really even more long-term than ice sheet loss. And so it takes tens of thousands of years to recover from this. We've also seen some pretty concerning developments about ocean circulation and water mass development around both in the Atlantic and Antarctica. And this can have feedback, especially in Antarctica, to then cause more warm water to be drawn back up to the ice sheet in a vicious cycle that causes more melting and then further slows down that circulation. This was really put into sharp focus at the Arctic Circle Council, which a very key and prominent climate scientist, Professor Stefan Ransdorf, who actually spoke at the pavilion just a few days ago, so I'd advise check that video out if you've not seen it. They delivered a letter to the Nordic Council of Ministers saying that really this risk seems to have been underestimated. And we're going to do a lot more research to really precisely constrain exactly what this risk could be for the massive implications, especially on Northern Europe. And so what I'm going to do now is pass on to Pam to explain how we went through 3 different emission scenarios for the future and really what the summary of these 5 dynamics means in terms of the negotiations really kind of beginning to finish off this final week. So I'll pass it back to Pam.
Thank you so much, James. So as you can see here, and also for those of you who are here physically, we took these 3 different futures to show the way the world's ice, the cryosphere, will respond. One are the currently national determined contributions, the NDCs, the pathway that we are on right now, if these are fully implemented. And we characterize that as about 2.3 degrees C. Depending on how you look at those, it could be actually quite a bit higher, potentially a little bit lower. But the consensus, especially from the UNEP emissions gap report, actually goes rather higher than that 2.3 degrees. If we continue with our current emissions, but even more so, if the current annual rise in CO2 in the atmosphere continues, that is our second pathway and choice. Because even though there have been all sorts of pledges and commitments, the levels of CO2 in the atmosphere are actually going up. And one could say this past year it accelerated. It will probably be a record year-on-year raise of the annual amount of CO2 levels in the atmosphere. That is probably because we have a very warm ocean that isn't able to absorb carbon dioxide as readily. And so that may go down in some, subsequent year. But regardless, it's very troubling. We're probably looking at between 3.5 and 4 parts per million growth. But the shocker in some ways is the high this year, which exceeded 428 parts per million a couple of times during the high April-May season, which is normally when CO2 is highest. That would put us on track for 3 to 3.5 degrees, at which point the cryosphere would respond very, very quickly in some cases and very aggressively to impact human communities and ecosystems. And then we have, of course, what we all want, which is immediate course correction back towards 1.5 degrees, which is still possible. It would require a huge amount of effort. But if you hear from anyone around here, and unfortunately some scientists are sometimes a part of that, it's almost, a matter of giving up and saying we can't stay within 1.5. We actually can. And on this, we follow the IPCC authors, people who are looking at the carbon budget, who are updating this on an annual basis. And their conclusion is that it's still within reach. And that is the scientific basis. We stick with that. So then in the report, we go through what the consequences would be for ice sheets and sea level rise, for glaciers and snowpack. And here there's a very stark difference in terms of whether there is glacier ice remaining and for how long, especially in the mid-latitudes. Sea ice, which has kind of a point of around 1.7 degrees, after which you're going to have an ice-free period, certainly in the Arctic, at any temperature above that. It may be brief, but certainly once you hit, say, 2.3 degrees, you're looking at 4 or 5, even 6 months of an ice-free period. And today is Permafrost Day, and that will have impacts, of course, on permafrost thaw, as well as loss of ice from Greenland. Antarctica is a little bit more uncertain, but we have seen, as James just showed, that Antarctic sea ice and Arctic sea ice both seem to have undergone a state change. And finally, permafrost, which you've heard a lot about today. Permafrost, of course, does not have a tipping point. That's one of the conclusions, actually, from this past year. But it follows temperature. And the higher we go, the more we lose. That's basically the way to put it. And the greater the emissions are on a multi-generational basis, and the greater infrastructure damage we see as well to Arctic communities, especially indigenous peoples. And then polar oceans. Very, very directly tracks with carbon dioxide emissions. And that is one of the strongest arguments, by the way, for any sort of, emergency geoengineering that you might hear about here in Baku, because that is being pressed forward. We will have a side event that actually goes through 5 of the most put forward polar geoengineering schemes at 11:30 tomorrow. Because a paper is out in preprint right now that goes through these, that has over 40 very eminent cryosphere authors working on that. But the amount of acidification is set by the amount of CO2 in the atmosphere, and that is actually the longest lived of all 5 of these dynamics. You see here and in the report, 30 to 50,000 years to buffer out. And so that, of course, is much too long a time for species that are susceptible to acidification to survive. So bottom lines, we can't negotiate with the melting point of ice. Some losses are now inevitable, and we will need to adapt to some degree of irreversible impacts, but we can still choose how difficult those impacts are going to be by rapid decarbonization. However, we must remember adaptation at some point has a limit that turns into loss and damage. And some parties here, especially in vulnerable countries, are saying after loss and damage comes loss of existence. And we have 5 years really to course correct. We need to course correct 2021 NDCs that are to be implemented over the next 5 years. And we definitely need to have very, very ambitious NDCs put forward in February or latest in Brazil that will put us on a path in the next implementation period, 2030 to 2035, so that we can keep that 1.5 degree limit in as much reach as possible. So we have here, in addition to James, some of the authors and reviewers of the 2024 report, and we're happy to take questions now about almost all of the dynamics. We'll do our best to answer. So turn it over to you for questions.
In a presentation a few hours ago in a side event, a scientist was telling the audience that the effects of glaciers melting are very different according to the place of the world when you are looking at it. So can you explain further which kind of effects, differentiate effects are you estimating according to different parts of the world?
I think that's going to be a James question.
Yes. Yes, that's a good question. So it's a complex question to answer because many, as you say, many parts of the world have different uses for glaciers and they're all melting at different rates. There's something we call peak water, which is as they melt more and more, initially they will increase the amount of water generated from melt, but then there'll become a point, a peak, which begins to decline away. And that timing will vary for different regions. Some places have already passed that peak, whereas others are actually still increasing. And so if you're working to adapt to try and make use of that water, it may be that in the short term you're having to plan for you having more water, and then in other places having to plan for less water. And this is a big problem if you're, say, investing in infrastructure like hydroelectric power, because it might mean that you're investing millions and millions of dollars into a big long-term infrastructure project, which then will become a stranded asset essentially when you begin to wane away. That's one. As well as that, you've got hazards such as the glacier lake outburst floods. These are meant to triple by the end of the century, and peak risk is by 2050. And so again, this varies spatially, but is also something which is quite hard to adapt to as well as this. And of course, you're thinking in much longer time scales, sea level rise. So glaciers, at least in the past, have been one of the dominant contributors to sea level rise. Now they're being slowly surpassed by the sort of big juggernaut of the ice sheet as they wake up and begin to contribute more and more. But you have this sort of multi-layered approach, which is going to be hard for adaptation, if you want to do it spatially and in time, but also some of these places, especially in some river basins in Asia, rely almost entirely on snow melt and glacier melt for their water. And once this is done, how are you going to survive with that? It's going to be a big challenge.
Yeah, and I thought I'd jump off that to give Flo a chance also, if you don't mind, to talk about, one of the things, again, when people talk about tipping points, to talk about the different regions of Antarctica and how they might respond differently. And feel free to go into Greenland as well.
Okay, so, well, of course, the location of each glacier is right.
And if you could talk to the people back there and not to him, so everyone can hear. Yeah.
Well, okay, so the location on the Earth of the glacier or ice sheet makes a big difference on the response they have on the climate system, of course. Because, of course, if the glacier is located toward the tropics, we respond differently to a glacier that is located at the polar areas. Right now, we have a polar amplifications in both hemispheres, more in the Arctic than on the Antarctic. And the big difference, for example, between Greenland and Antarctica is that at the surface of Greenland, we have a lot of melting occurring during the summers. While in Antarctica, the mechanism is completely different. You don't observe a lot of surface melt because it's still very cold and located at South Pole. But it's melting from below by the warming of the ocean, actually, that brings a lot of heat to the Antarctic margins, actually. So the glaciers are melting because of different processes. Could be atmospheric directly, oceanic processes, like in Antarctica, but also locally in mountain glaciers, the orientation of the glaciers. If they are northward oriented or southward oriented, makes a big difference to the solar radiation that they take, actually, and so the amount of heat that they absorb on the ice, and then the velocity, the speed, the response to this, and how long they will melt it for, actually, which depends on how much heat they really absorb. And so that's why we have so strong difference in how much they melt and how fast they melt, and when this melting will be irreversible, which brings us to tipping points. So it means that at some point, this melting will be not able to be recovered by the next season of snowfall, for example, and then it will become irreversible. And so the glaciers or ice sheet, they will retreat and retreat and retreat and retreat. So irreversible. And such tipping points varies a lot based on the factors that I just mentioned, actually. So could be now, could be in a few decades, could be in a few centuries. Some regions of Antarctica already triggered the tipping points. Some glaciers also already has theirs in different regions of the world, like in the Alps or in Iceland, for example, they already have entire glaciers that disappeared. In the Himalaya, the situation is highly critical. Whilst in some other areas, the glaciers are still fairly stable, which means that they will start melting a little bit more in the future, but they will melt for sure if the temperatures still rise.
One more point to add to that is, yeah, as Chloe said, basically one of the biggest uncertainties about how to predict this in the future was which emission pathway we take. And so we're still not sure if we're going to suddenly manage to have some radical action by the guys over there and actually course correct to a low emission pathway, or whether we're going to keep shooting up, keep emitting more and more, because it makes a drastic difference in the end result, both for glaciers and for ice sheets at a very long time scale. So this is really why we are here for, pushing the importance of these ecosystems and the Earth system that is the cryosphere policy.
So I understand the scientific perspective here, so you operate a lot with data. How do you think when it comes to communicating the message to policymakers, to ordinary people, what tools are you using to make them palatable and digestible so they actually take this on? Because I think the role of civil society is incredible. They are the ones who instigate change. So probably challenging question, but I really like to.
Well, I mean, part of it you see around you, right? And we're very, very lucky this year because this is at the very entrance of the pavilion area. And I think it's fairly safe to say that whatever the number of people who came to this talk is the number of people who at least passed by and for a moment saw this exhibit. The other, of course, is the State of the Cryosphere report, because it is put in what we call policymaker language, which means we try to pitch it at a level that really a high school, a secondary school graduate would be able to grasp. And we try to relate it to policy. Parts of it get very, very, dense in some ways, but the typical example that I use is actually with ocean acidification, because we talk about acidification, we talk about corrosive waters. It took me forever to get the scientists on that chapter to accept that, because they want to talk about calcium carbonate. Yes, exactly. Calcium carbonate absorption. No. Thank you. Speak up.
I think it's calcium carbonate depletion.
No, it's actually calcium carbonate saturation. That's what you're looking at. But who understands what that is, right? So we use the word acidification or corrosive waters so that basically it's understood that shells are being dissolved, that the basic real life cycle of these organisms is being affected. It actually affects metabolism even of non-shelled organisms. So it's an important factor. And another important factor, again, on Permafrost Day, our understanding is that some of this is coming. Yeah, do you want to address that? You're nodding.
From a high level point, but maybe you can direct me at where you were going. One thing that we always like to think of as scientists, and a popular slogan maybe you've heard, is what happens in the cryosphere does not stay in the cryosphere. It directly affects climate, both now and long term, and our weather. So every time we think of severe weather events happening on our own backyard, this is directly related. And it's only going to get worse.
Basically connecting the dots. Knowledgeable ordinary people, they really don't understand.
Yeah.
Exactly.
It's challenging.
I mean, I would say sort of provocatively, pictures and stories, because, for example, sea level is currently rising at 4.5 millimeters per year. Does that mean anything to you? Of course it does. But when you go and speak to someone from an island like Tuvalu, for example, and they show you a picture, and they're like, right, we can't grow the food we used to grow anymore because the ground is now too salty. We can't get drinking water out of the wells we've drank out for years because it's too salty. And now we're having to buy food in from our other islands and things because we physically can't afford to deal with that 4.5 millimeters a year. And so having that narrative is incredibly important to connect it to someone. So I mean, Catherine Hayhoe says you've got to connect the head to the heart to the house. So you've got to get, make them realize what's going on, make them realize how it affects them, and then give them the tools to do something.
I think connecting the dots and translating.
Anybody else want to compete with the coffee machine over there? Going once, going twice. Okay, thank you very much. We have a very full schedule again tomorrow, as I noted. And if any of you are, here as scientists wanting to also engage in the negotiations, we do what we call cryosphere coordination meetings at 8:30 every morning. If you're up to it, feel free to come and sit in on those, and you'll get a bit of an update as to how things are going there as well. Here, yes, exactly. Most welcome. Okay, well, thank you, especially to our scientists. Thank you so much. They put a lot of time into this.